Let's learn about tension forces. Tension force is a pull via a rope or a string or a cable. Tension forces have a few unique properties. Tension force always acts along the line of that cable or string or rope. It exerts force on both ends. So there's an object that's being pulled, that experiences a tension force. And there's an object doing the pulling. Maybe you're pulling on a cable, but the object doing the pulling also experiences a tension force. And additionally, the force is the same throughout the cable. It doesn't vary from place to place. This is assuming a massless cable or rope or string, which is what we'll assume. That's not super realistic, but as long as the rope or string is thin enough, it works just fine. So imagine that you're pulling a car via a rope. Let's draw a quick free body diagram for this situation. When dealing with tension forces, it's really important to keep the object of interest in mind and to remember that the object of interest only experiences forces that are directly acting on it. So here's what I mean. If our car is our object of interest, obviously it's experiencing gravity force from the earth pulling down. It's experiencing a normal force from the ground. So gravity force of earth on car, normal force of ground on car. And now there's the tension force. That tension force is not caused by the person. The tension force comes from the rope. So a common mistake people do is they'll say, oh, there's a force on the car caused by the person. But when we're drawing free body diagrams, keep in mind it's only the object that's directly exerting the force on that car. That's the rope. This is how tension forces work. If you wanted to look at the force that the person was providing, you would draw a free body diagram for the rope. If you wanted to look at the force on the person, you draw a free body diagram for the person. But as far as the car is concerned, this tension force comes from the rope, not from the person. Okay, let's do a series of 4 examples from your textbook. Your textbook calls them case 1, case 2, case 3, and case 4. So case 1 is vertical tension forces on a static object. And the setup looks like this. You're essentially hanging a block from the ceiling via a rope. So let's draw a free body diagram and analyze the tension force. Standard XY, vertical, horizontal is a good coordinate system. We place our object of interest, that box at the center. Gravity is pulling down. And there's tension force from that rope on our block. And now Newton's second law says that the sum of the forces on the block equals ma. But that block is just sitting there. There's no acceleration. So we've got T minus W equals 0. So the tension force, if I drop these subscripts, equals the gravity force. It equals mg. All right, case 2. Vertical tension forces on an accelerating object. So this is a block hanging from the ceiling of an elevator. All right, imagine that's an elevator. There's the big elevator cable. We'll make it look like a thicker cable. And it's accelerating the elevator upward. And inside that elevator, someone tied a block to the ceiling with a string. Because why not? So let's draw a free body diagram for that block. It's going to look really similar to the example we just did, because you've got gravity going down, and you've got a tension force of the rope on the block pointing up. I know I keep saying string or rope or cable, it doesn't really matter, whatever you want to call it. So this free body diagram looks pretty similar, except this time we're going to find that tension force is stronger than it was in the previous example. Because when you analyze the situation via Newton's second law, that's not 0 anymore. This whole contraption is accelerating upward. So we can't cross that out. We've got T minus W equals MAY. So T, and I'll drop all these subscripts, equals MA plus MG. So in our previous example, where this thing was sitting still, the tension force was just mg. But now, it's mg plus ma. There's greater tension, because it not only has to support the block's weight, but it has to accelerate it upward. If this elevator were accelerating downward instead, this A would be negative, and the tension force would be smaller. That reminds me, tension forces are always pulling. You can't have a rope or string that's pushing. So if this downward acceleration were very large, at some point you would reach tension equals 0, and you can't ever have negative tension force. It can't push. The string will just squish and collapse. All right, let's do case 3. This is two tension forces at symmetric angles. Now we're starting to get into stuff that's related to structures, and also like biomechanics. the types of, these two examples, case 3 and case 4, are examples of static equilibrium, and this is useful in architecture. It's also useful for understanding forces on joints and bones and ligaments and so on. Alright, so here we still have a block that we're hanging, but this time it's via 2 cables. I didn't draw this very well, but the idea is that they each make an angle theta with respect to the vertical. So that dotted line in the middle is not a cable, that's just me trying to draw a vertical line so that I can show you what those angles are that the 2 actual cables are at. So here's the free body diagram. Object of interest. Here's our friend, the gravity force. And now we've got 2 tension forces coming out at the same angle. So I tried to draw that symmetrically, I didn't do it very well. But these angles are each theta. And if you think about your right triangle geometry, the x components here are going to get sine, and the y components are going to get cosine. Think about adjacent and opposite and where that angle is drawn. So in the x direction, we have, oops, there's t. Let me write T1 from cable 1 on the block, and this will be T2 from cable 2 on the block. Then we've got T1, B, the x direction gets that sine, and T2b also gets a sine, and also gets negative because it's pointing to the left. And by symmetry, because this problem is symmetrical, the cables make the same angles, we can assume that these 2 tension forces are the same as one another. So we can replace each of them with just T. And that leaves us with the very interesting and not helpful mathematical statement, 0 equals 0. This is true, but not useful. True, but not useful. What will be useful is the y direction. Sum of the forces equals 0 in the y direction because this thing is just sitting there, not moving. And we have t cosine theta plus t cosine theta, minus w equals 0. So I got rid of these subscripts and I replaced those with just t, because we already said that by symmetry, they must be the same value. And I got rid of the subscripts on the w too. So we have 2t cos theta equals w, which is mg. And that means that the value of the tension force is mg over 2 cos theta. And that's an interesting result because it's showing you that the larger theta is, the bigger the tension force is. When this angle is small, not as much tension is required in these strings to hold the block in place. As that angle gets larger, these strings are going to go way out here, and they are going to have a lot more force on them to be able to hold the block up. That's what this equation is telling you. Okay, one more. Case 4. We again have a block held in place by 2 strings, but the geometry is kind of weird this time. It looks like this. Here are 2 strings. There's one that makes an angle theta with the vertical. That's just a vertical line, not a string. And here's the other one. It's purely horizontal. You can see why, if you didn't have this here, the block would just hang straight down vertically from the string. But the fact that it's connected with the string to the wall over here means that this string can be at an angle. Structures. And unlike case 3 with our 2 strings, we can no longer assume that this problem is symmetrical. We can no longer assume that the 2 tensions are going to be the same. So what's going to happen in algebra is we're going to have 2 unknowns. The 2 tension forces will both be unknown, and we'll have to use 2 equations, the x and y equations, along with some algebra to solve for our 2 unknowns. So let's do it. Here's our free body diagram. There's the block. There's T1. There's T2, and there's gravity. I didn't bother with the subscripts this time because I think we know what they should be. That's the gravity force of the earth on the block, that's tension force of rope 1 on the block, that's tension force of rope 2 on the block. I'm saving myself some writing. Okay, so let's do Newton's second law in x and in y. That'll give us 2 equations to solve for our 2 unknowns. This is a static equilibrium problem, which means nothing is accelerating. So the right-hand side there is 0, ma equals 0. And as before, this x component of tension 1 gets sine because it's the opposite side of the right triangle. T2, fortunately, we don't have to do any trigonometry. It's completely along the x-axis. In the negative direction. So you can see now what I mean about this algebra situation. This is one equation with two unknowns in it. You can't solve for a final value of either T1 or T2. We only know them in terms of one another. So we might write T2 equals T1 sine theta, and then just keep that there, keep it in mind, and we'll use it in algebra after we start doing our analysis for the y direction. So in the y direction, those forces equal 0, the block's not accelerating in y either. And we've got the y component of T1 that gets cosine because it's adjacent to that angle. Gravity is pointing down, we give that a minus sign there. And so we have a relationship that T1 cosine theta equals mg. And this we can solve. So now we know that T1 equals mg over cosine theta. And we can also now solve for T2, because T2 equals T1 sine theta, or mg over cos theta sine theta. Sine divided by cosine is tangent, so T2 equals mg tan theta. All right, and that's how you analyze that problem. Now, this is really our first example of, I think it's our first example of seeing a problem where there are, it's like a system of equations. So remember from algebra class, if you have a certain number of unknowns, like if you have two unknowns, you need at least two equations to solve for those two unknowns. And in this unit on Newton's laws, we're going to get into problems where there are several unknowns and you have to set up several equations and solve them as a system of equations, and that can get pretty tedious and intense. Fortunately, there is kind of a shortcut for doing problems like that, so stay tuned for those lessons.